Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207 Calculus 2. Hopefully you guys had a good Halloween weekend and you're ready to jump back into it. Glad to have you back. Seems like almost everyone's here. We have a couple people missing, but let's actually get started. Lots of interesting things to talk about today. Well, at least I think that the next 3 lectures are going to be pretty fun. I'm pretty excited about them. I don't know how far we'll get today, but show you something cool by next lecture for sure. So we are going to continue our story about series. Series, very important topic. Last time we kind of wrapped up with going over the strategies for approaching series. So first of all, knowing whether a series converges is going to be important in general. Also knowing about whether it converges absolutely, conditionally, or diverges, being able to actually talk about the type of convergence a series experiences is going to be very important in general. So that being said, I will ask you directly whether or not certain series converges, and that presents a challenge in the sense that for a random series, how do you even know what series test you're supposed to be doing? So here we went through 10-ish or so series tests that can determine if a series converges. The geometric series test not only tells you about when a series converges, but it can also tell you to what. And because there are so many tests, it can be confusing as to when you might use which, just in the same kind of way that when you knew a bunch of integral techniques, it was kind of confusing when to apply which. And you don't want to work harder than you have to. So last time we went over some strategies of how you'd actually apply those. So hopefully you remember all of that. Basically, when it comes down to it, you always go with the test for divergence first. Other than that, it depends on what you're asked. So if I ask you what something converges to, it's pretty much going to be geometric in general, because that's the only test that tells you what something converges to. If you're asked for absolute versus conditional convergence, I showed you the strategy last class for doing that. Other than that, you kind of look for specific forms like geometric series or alternating series or P series. If something is rational or close to rational, or it's kind of just weird, so you'd rather have something other than what you're looking at, comparison theorems can be very useful. If you have factorials or exponentials, the ratio test is going to be useful. And we're actually going to see another use of the ratio test today and continuing into next class as well. The root test is useful if you have like the nth power or a constant times n as the power. And it's also worth noting that the ratio test and the root test behave very similarly. So if one is inconclusive, the other one will be as well. So you'll never really try both of them in general. If you notice that you have a function that's easy to integrate, hopefully at this point you're very good at integration and you can actually just look at something. You know what, if this was an integration problem, that would actually not be so bad. Whenever you notice that, and you can verify that the function is continuous on the interval, it's non-negative and it's decreasing, then the integral test is a useful thing. And that was basically it. It's not as involved as with integrals, but it's still very important to notice the strategy, because things can get confusing when you have a lot of options to deal with. That being said, we're going to move on to a very important topic, although we're not going to spend a lot of time on it, and that is called the topic of estimation. We are going to learn how to estimate a particular kind of series. So there are a bunch of topics in your textbook about series estimations, sprinkled through sections 11.3, 11.4, and 11.5. We'll only be focusing on one of them, the one in 11.5. So focus. Okay. Now, that being said, estimation is a very important thing in general. So this is something that I've actually brought up before, as well as I brought it in my Calc 1 class, in my pre-calc class, because what happens is a lot of students, especially if they come up in a system that is geared towards test performance and just teaching to the test and things of that sort, you can come away with an impression of mathematics that is more or less like black and white. Oh, you know, there's only so one way you can do this, and you have to get to the right answer. There's only one answer, and blah blah blah. In reality, this is not the case. In reality, being able to estimate things is super important. In reality, sometimes having a good way to estimate an answer is more important than coming up with the actual answer itself. And oftentimes it's more useful in general. So sometimes when we can't even get to the answer, it's very important for us to know how we can guess something that's close to the answer. And it's also important for us to know how good is that guess? Like, how far away from the actual answer am I? Right? These are very, very important considerations. And whenever math is applied in the real world, you're always using these considerations. So I know it seems very pervasive, but you have to realize that in the real world, the concept of a real number can't really exist, right? So you start to think about something like pi in real life, right? What is it? Do you ever actually use it? Can you ever actually encounter it? And the answer is actually no. Pi is a very ideal concept. The idea of a real number is an ideal concept. The rational numbers are far more realistic in the sense that they're the ones that you would use. So whenever, for example, you're using in your calculations, you're using pi, you type it into your calculator or into a computer or something like that, you don't actually use pi itself, right? Use an approximation of pi. Your computer will round it off to 15 decimal places or something like that. And once you have a 15 decimal place number, you can write it as a fraction. Pi is not a fraction. However, in the real world, you'll never actually be able to write out the entire expansion of pi. It's impossible, right? You'd have to be able to write out an infinite number of digits, right? So if you're in a situation where the answer is pi, sure, that might be the ideal answer, but in the real world, you're never actually going to use that answer. You're going to use some approximation of it. And that makes approximation theory very, very important. And when it comes to series, this is also true. So we're dealing with infinite series, and it's very important for you to realize we can't actually add up an infinite number of things, right? We don't have the time, we don't have the power, right? And there are times when it's very hard to figure out what a series converges to. And then there's the idea that even if I could figure out what it converges to exactly, it's probably not as important as for the accuracy that I need for this particular calculation or application. So being able to estimate series is an important idea in general, and that's what we're going to talk about, right? So pretty much the TLDR of this is finding out what a series converges to, very difficult in general, right? However, we can approximate series. And how do we approximate series? We can approximate it with partial sums. So instead of adding up an infinite number of terms in the series, you add up a finite number of terms. Add up the first 100 terms, the first 1,000 terms, the first 1 million terms. Now, that might sound like a lot to you as a human being, but to a computer, adding up a million numbers is really no big deal. So we can actually use partial sums to approximate series, and that's what we're going to talk about. Right now, we have estimation theorems that pretty much will tell you how good a certain partial sum is to approximate a series. Okay, so that's the idea. Computing series, very important. Perhaps even more important is being able to approximate them within some desired degree of accuracy. The main tool that we will use to approximate series is their partial sums. And we basically want to figure out, well, how many terms do I need to add to get a good enough answer? How many terms do I need to add to get close enough, right? And it turns out that for different series tests, there are a variety of techniques and there are a variety of answers to that question. However, our focus will be on 11.5, where we're going to talk about alternating series specifically. So I'm going to tell you how you'd approximate alternating series. In general, but if I had more time, I would probably cover 3 particular cases. I'll talk about the alternating series, how to approximate those, but I'll also talk about series where you can use the integral test. How would you approximate something like that, that you can use the integral test for? But we're going to skip this. We're also going to skip using the comparison test or Any series that you can tell converges by the comparison test, there's a certain test that goes along with that that helps you to come to approximate the series. Similarly, if you use an integral test, there are certain theorems that tell you how to make approximations once the integral test is what you got to work, etc. In our case, we're just going to look at alternating series and how to approximate those guys. We know how to tell if an alternating series converges. You look at the AN term. If it's positive, decreasing, and the limit is 0, we know that the alternating series converges. Saying it converges to what is a lot harder. And so that's what we're going to get at. Now, for this, we will actually need some more terminologies here, some of which you already know about. Okay, so here's a series, right, that I'm looking at right here. Okay. Suppose that is a convergent series, which means I can write it out like this, that you see here, right? So it's A1 plus A2 plus A3 plus A4, going on forever, right? So we've seen this before. We call the sum of the first n terms the nth partial sum, right? So if I add A1 plus A2 plus all the way up to AN, we call it the nth partial sum. This is the sum of the first n terms of a series. I did not give you a name for the tail, what's left over. So now I'm going to identify that. This is the guy that we call the remainder term, right? So the sum of the first n terms is called the nth partial sum. Everybody else, we call that the remainder term. It's what's left over after you take out the first n people, right? So you can have the nth partial sum as well as the nth remainder term, right? So now in general for infinite series, of course, the remainder term is going to have an infinite number of things in them, right? And so it's also worth noting that if S is the actual sum, then if I were to take the partial sum and subtract it, right, and move it to the other side, that will actually tell me, give me a measurement for the remainder term, or what is left over after I subtract the partial sums from the actual sum, right? Now, this number S is very hard to get a hold of in general, right? So being able to find what that S is, very hard. However, being able to find what Sn is, not so much, right? So we can actually do that with series. You just need enough processing time, which we can do for a lot of things. Okay, so here I just want to define the remainder term because it is something I'm going to be using a lot more often. But it's just pretty much everyone besides the sum of the first n terms, essentially, right? So what that means is, as I said, the magnitude of the remainder term can be computed by figuring out the difference between the actual answer and the sum of the first n terms of your series, right? So I can estimate the remainder term. And one way you can actually interpret the remainder term is like it's an error. It's the difference between the actual sum and the sum of the first n terms, meaning we can actually use the remainder term as a measurement of how good our approximation by the first n terms is, right? The smaller Rn is, the closer we are to the actual answer. And so at the end of the day, we really want to find a way to actually measure the Rn term. How big is it? Because how big it is tells us how far we are from the actual answer, right? So that's just some new terminology. Now on to some estimation theorems. So the first one is the alternating series approximation theorem. And this is the only one we will be doing in this class. Only estimation theorem will do. Right? So I'm not going to ask you about approximating anything else other than an alternating series. Okay? So you won't need to know anything, not even in a bonus. I'm never going to ask you any of the other ones, right? So this is the only one we need to know. Okay? So that's super important. Take a screenshot of that. And of course, I'm going to provide the notes later. Okay? So the alternating series approximation theorem, it turns out the alternating series test is actually pretty straightforward, pretty simple as far as all the test goes. Just comes down to doing a check of a couple conditions and actually taking a limit. Coincidentally, the alternating series approximation theorem is also a pretty easy theorem to apply and to know when it works. So suppose you have an alternating series, right? So remember, we can write an alternating series in one of two ways, something like that. And suppose it converges. So we can do the alternating series test and we know this converges. Then it turns out this is true, which is really amazing. It's very amazing that that actually works out. So here's basically what that says. It says that the size of the remainder term, which is the difference between the sum and the nth partial sum, is always going to be less than or equal to the an plus first term. In other words, the magnitude of the n plus first term tells me how far away from the actual answer the sum of the first n terms are. So if I add up the first 10 terms of an alternating series test and I want to know how close am I to the actual answer, all I have to do is look at the 11th term. The size of the 11th term is an upper bound on how far away I am from the actual answer. If I add up the first 100 terms, how close am I to the actual answer? Look at the 101st term, right? No matter how many terms you add up, all you have to do is look at the magnitude of the very next term, and it actually tells you how close you are to the actual answer to within some degree of accuracy. That means you're at most that magnitude away from the actual answer, which is pretty neat, pretty useful. In fact, we do know something else, which I'll talk about today. I'm not sure how much I'll actually test you on this, but we can actually know about the sign of s minus sn, right? It's actually the same sign as the first unused term. So whatever sign the an plus first term carries, that will be the same sign that s minus sn carries. So if the an plus first term is a negative number, what that would mean is that s minus sn is also negative, which will tell you that the partial sum is actually larger than the actual sum, etc. So we can actually know on which side of the coin. So the an plus first term will tell you how close you are to the actual answer within some degree, and you can actually know which side of the fence you're on. So for example, let's say you're doing an alternating series, you add up a bunch of terms, and you look at the magnitude of the very next term. And let's say that magnitude is 0.1. What that means is you're actually within 0.1 of the actual answer. The actual answer will either be 0.1 larger or 0.1 smaller at maximum of what your current answer is. And if you know the sign, you'll actually be able to tell, is it larger or smaller? So that's actually pretty useful. So the alternating series approximation theorem, pretty easy and pretty useful. So let's actually do a simple example of actually applying this. Let's actually look at this example. So we know that this series converges. This is the alternating harmonic series. We showed that this converged last time, or maybe time before last, I don't remember. But it's a very straightforward application of the alternating series test. An equals 1 over n, it's decreasing, it's positive, and the limit is 0. So it actually converges conditionally by the alternating series test. We know that this does not converge absolutely because, again, in absolute values, if I put each term in absolute values, we get the harmonic series. Okay, so here's an example. We have our alternating harmonic. I would like us to find S4, and then we are going to do some approximations. Okay, so S4, this is just, okay, so here, remember the alternating harmonic. As written here, it's going to be -1 plus a half minus a third plus a fourth. My hands are pretty shaky today. Probably too much caffeine. Right? So that's the series. Okay. Now I want S4. So S4, well, that's just the sum of the first 4 terms, right? So that this just A1, and I mean, you don't have to write this down. I mean, it should be clear. But this is just A1 plus A2, or to follow the signs here, minus A1 plus A2 minus A3 plus A4, right? Where I'm thinking of this guy as my AN is 1 over n. So that's all I want to find. So here, that's going to be -1 plus a half minus a third plus a fourth. Let's actually calculate that, adding fractions. The LCD here is 12. -1 is 12 over 12. A half is 6 over 12. A third is 4 over 12. A fourth is 3 over 12. So that looks like -7 over 12. That is the sum of the first 4 terms. Now, of course, for your education, for some comparisons that I'll be making later, let's actually see closer to what this is. Right, so that would be your answer on a test or a quiz, but let me use my calculator to just make some comparisons later. Right, so this is roughly -0.583, and the threes continue forever. Okay, so that's my approximation using the first 4 terms. That is S4. Okay. So far, any questions so far? Are we doing okay? Okay, so here is the follow-up question. I've now computed the sum of the first 4 terms of this series. How good an approximation is S4 for the series? Meaning, if theoretically I was able to add up all the terms, add up an infinite number of terms, right? And I would get an answer. How close would -7 over 12 be to that answer? And what do you guys think? So if I want to actually measure the error, this is just the size of the remainder term, right? Which in this case, it's R4, okay? What can you tell me about R4 according to the alternating series approximation theorem?
Wouldn't it be at most 1/5?
Be at most 1/5. How did you get 1/5?
It's A of 5.
A sub 5, right. So this here is the difference between the actual answer and the sum of the first 4 terms. We're told by the alternating series approximation theorem that this is going to be less than or equal to the magnitude of the very next term, which is A5. And what is A5? Well, that's just 1 over 5, right? So that is, right, pretty much 0.2, i.e., the difference between the actual answer and the sum of the first 4 terms, it's going to be less than or equal to 0.2 in magnitude. Interesting. So if you only care about being accurate within 0.2, adding up the first 4 terms is just as good as adding up all infinite number of terms, right? So if you have a tolerance for 0.2, you are fine with adding up 4 terms, which is a lot nicer than having to add up an infinite number of terms. Okay. Is S4 larger or smaller than the actual sum? Okay. So this is talking about pretty much this statement that I made here. Right? And this kind of follows directly from the fact of how Rn is defined. It's just the difference between Sn. Okay. So notice here, what is the sign of A5? Right. Notice here, the sign of A5 is minus. This means the sign of S minus S4 is minus. this means S4 is larger or smaller than the actual sum?
Larger.
It's larger, right? Because if you take the actual sum, you minus the first sum of the first four terms, you get a negative number, which means you have to take a smaller number and subtract a larger number. So S4 is larger than the actual sum. So I know that S4 is about, at most, I should say, 0.2 away from the actual answer. And now I know what direction that's in, right? So S4 is going to be about 0.2 at most larger than the actual answer I want, right? So you might be in a situation where you want to err on the side of being a little bit more or a little bit less. And this will actually tell you, well, if you really want to be a little bit less for some reason, S4 would not be a good choice. You'd probably bump it up to S5 or something of that sort. Right? So it's actually larger than the actual sum. Okay. Now, let's make some comparison for fun. Now we'll see. Now I did mention this a couple times, but we're actually going to prove this. Probably not today, but by next class for sure. We'll see that this sum is actually equal to minus ln of 2. Very strange answer, but that's the actual answer. And let's actually look at what that is. So again, you wouldn't be required to do this because I'm actually using my calculator. But let's actually see what that is. This here is minus 0.69314718. Meaning S minus Sn, the actual difference, what did I have here? Minus, I believe it was 7 over 12. 0.10981 ... So we actually did better than 0.02, which is fine, right? We said we'd actually be less than or equal to 0.2, and we actually are. So by adding up 4 terms, I'm actually within 0.1 of the actual answer, right? Worst case scenario, I was at 0.2, but we actually legitimately did better than that. We did twice as good as we expected to do, which is not too shabby, right? So someone's adding up an infinite number of terms. If you only care about a tolerance of being 0.1 accurate, you can get away with adding up 4 terms. And knowing that is super important and super useful, right? And at the end of the day, when you do use your calculator or you're using Wolfram Alpha or something like that, and you plug in a series into Wolfram Alpha, or you plug in some other problem entirely, and Wolfram Alpha actually converts it to a series without telling you to actually compute the answer. What Wolfram Alpha does is it doesn't actually add up an infinite number of terms, right? Pretty much what Wolfram Alpha does is it adds up enough terms so that it will be accurate to however many decimal places it wants to display to you. So it's going to decide, okay, well, if I want to display 12 decimal places to the user, what I'm going to do is just make sure that I approximate this series within 13 decimal places, and then I'll just round up and show the 12th decimal places answer to the user, right? And of course, Wolfram Alpha will go through some sort of approximation theorem to figure out, oh, I need to add up this many terms to be able to show an answer this accurately, right? And it's pretty cool, right? So this theorem here works with the alternating series. And that's the actual answer. Now, why is the sum minus ln2? We're actually going to see this later on. We actually need some more machinery though, but we will actually prove that this is minus ln2. But yeah, it's pretty cool that I could just add up 4 terms. It can get reasonably close to the answer. And I can actually know how close to the answer I actually am, which is pretty cool. Now, let's suppose this is like after the fact. So let's say I add up a bunch of terms and I can figure out how close I am to the actual answer. But let's say I was in a different scenario where I was actually told how accurate I want to be in the beginning, right? So let's say ahead of time, I know how accurate I want to be. For whatever reason, my tolerance is 0.01. I want to know an approximate answer for this series to within 0.01 accuracy, right? I want to be accurate up to 2 decimal places, or at least for sure on the first decimal place. Right, so that's the challenge. Now, of course, in this class, whenever you have to do something like this, I will tell you what tolerance you want, what accuracy I desire, whether it's by 0.01 or 4 decimal place accuracy, etc. I will tell you. However, of course, in general, it's really context dependent. So based on whatever field you're in or why you're doing the calculations or what you're doing the calculations for, you'll have your own reasons for choosing a certain accuracy. So if any of you are going into engineering, for example, and you want to go into civil engineering, there are always laws that say how safe something should be. So if you're building an elevator and you're making sure that it can hold at least 1,200 pounds, right? You don't want to build an elevator that holds exactly 1,200 pounds because 1,201 pounds and suddenly everyone's dead. You don't want that. So there's a cushion, right? So whenever you're in certain disciplines, there might be a legal requirement as well as just best practices requirement to always have a certain percentage leeway. So context dependent, you'll always have this sort of tolerance in your mind that you would want to aim for, right? But we're not going to deal with anything that specific. So whenever we have a tolerance, I will give you the tolerance. I'll tell you how accurate I want you to be, and you just have to figure out how we have to do it. So let's say you're Wolfram Alpha, someone gives you a series, an alternating series. They want to be able to approximate that series to within 0.01 degree accuracy. How many terms do you need to add up and display to the user to be that accurate? Do you need to add up 1,000 terms, 1,000,000 terms, 15 terms? Like, how do you know? So any ideas how we would know? How many terms would I need to add?
I'll just keep adding them until the next one is within 0.01, and then it's the previous one.
Right. So of course, there would be a quicker way to actually figure that out, right? Just go to the next guy, right? Just use the next guy as the thing. So you wouldn't just keep going and adding up. Although if you're a computer, that might be something you'd want to do because you're not afraid of arithmetic if you're a computer. But we can be a little more sophisticated by hand. We can just go to the next guy because we know that's what we're going to want. So at the end of the day, we are going to want to focus on the an plus first term. So now we know that the difference between this guy is less than or equal to the an plus first term. So all we want is for the next term on whatever n is. I don't know what n is in the beginning, but I know whatever it is, the an plus first term, I would want to be less than 0.01. Because that would guarantee then the alternating series approximation theorem gives that the difference in S, which I know is less than or equal to an plus 1, that is going to be less than 0.01. So I can actually guarantee how good the approximation is by just finding the term that will make the approximation work. Just focus on the an plus 1 guy, so the n plus first guy. Now, in our example, we're using the alternating harmonic here. Our an is just 1 over n. So an plus 1 is 1 over n plus 1. Just replace all n's with n plus 1s in the given formula. So here we want 1 over n plus 1, I want that to be less than 0.01. And now I just have to solve this inequality for n. Can flip both sides. This means that n plus 1 needs to be greater than 100, which means that your n needs to be strictly greater than 99. So 100 terms is needed to be guaranteed 0.01 accuracy. Now, as you saw earlier, we might actually be able to get better than this sooner, but we won't know for sure until we actually look at that and compute it. But I know worst case scenario, if I add up 100 terms, I'm guaranteed that I'm going to be within that error, right? Now, I might even meet that error at the 78th term or the 85th term or some term before, but I won't know for sure, right? The theorem only guarantees this accuracy. So again, versus adding up an infinite number of terms, adding up 100 terms isn't that bad for 2 decimal places of accuracy. But that's how you would do it, right? So pretty straightforward with the alternating series. So the alternating series approximation theorem, pretty useful. You have an alternating series. You can add up the first n terms. That will give you a number. You want to figure out how good an approximation that number is for the entire series. All you have to do is look at the magnitude of the very next number, right? That will tell you worst case scenario how far off you are. If you want to know if you're a little bit bigger or smaller, then the sign of that next term will tell you whether you're bigger or smaller. If the sign is negative, it means you're a little bit bigger than the actual answer. If the sign is positive, you're a little bit smaller than the actual answer, but we know what magnitude we need to follow. Now, of course, if someone gives you a tolerance ahead of time and you know what tolerance you need, all you need to do is just realize that your upper bound for your error is by the magnitude of the n plus first term. So all you need to do is just make sure the magnitude of the n plus first term is less than your tolerance. That essentially comes down to taking the original sequence formula for your series, replacing all n's with n plus 1s, and solving for n. You do that, and you're guaranteed to be that accurate. So you plug in to Wolfram Alpha. Hey, here's the alternating harmonic series. What does this add up to, Wolfram? Wolfram is like, well, I'm only going to give this person 1 decimal place accuracy. What Wolfram would do is it would only add up 100 terms, and then it would give you the output, like minus 0.7 or something like that. And yeah, it's 0.7, right? It was 0.69. Yeah, it will give you like minus 0.7 as the answer by adding up the first 100 terms. And you're like, wow, Wolfram, you're amazing. You just added up an infinite number of things and gave me the answer. And no, Wolfram never reveals its secrets. Well, now I'm exposing all. Okay, so that's it. So this is a very important problem type. It's very, very important in principle. As I said, estimation is a big thing. It's a big deal. However, in this class, when it comes to estimating series, this is pretty much the only thing I would ask you about. It's never really going to get more complicated than this, actually. As long as you remember that we can only do this with alternating series, and this is how it applies, you should be fine. Should be straightforward. Like I said, I left some notes here, but we're going to skip these. Yeah. Ignore everything onwards, right? If you're interested, you can read it, but I'm not going to test you on any of this, right? So there are ways to put bounds on the remainder term if you use the integral test. There are ways to put bounds on the remainder term if you use the comparison theorem. There are ways to put bounds on things depending on what test you can actually get to work. There are estimation theorems that will go with that test to actually tell you how good the test was if you were to use partial sums. So yeah, and that's that. That's what we'll see about estimating theorems here. Any questions before we move on? Anything that was not clear? Okay. Okay, let's move on. Now we're also going to talk about a very heavy hitter. We're now going to start our discussion, and this will continue for the next 3 or 4 lectures or so. Power series, very important type of series. And there are several important classifications of series, but the power series is one of the most important ones. If you go into a class like differential equations, you'll see other things like Fourier series and things of that sort. But the power series, very, very useful, very, very important kind of series. Now, you may have noticed here that we threw X into the mix. So now we're not only have series with N's in them, we have X's in them, right? And I'm going to just tell you the definition of a power series right now. And in hindsight, we're going to look at what this might signify, why we might think it's important, etc. Right? So for now, this is just a blank definition of a power series. You can take a screenshot of it. The power series is defined in terms of being a certain form, kind of like how a geometric series is defined in terms of being a certain form. Okay, so a power series is any series of this particular form. Sum from n equals 0 to infinity of Cn times x minus x naught to the n. Your Cn is a constant. We interpreted it as a constant. Of course, your series thinks of the n as the variable. So that's worth mentioning. So the series is changing the n's, right? It plugs in n equals 0, then plugs in n equals 1, then plugs in n equals 2, and it keeps going, right? But it's actually, by doing this, it generates a list of numbers. So to our perspective, any function of n is going to be a number, right? It's just some member of the list, right? But the series is telling you how to calculate that. The variable from our perspective is going to be n. So n is x is x. X is a real variable, so it's just a real number, but we think of it as a variable. We can change the value at will for us. X naught is a particular real number, so x naught is also a constant. Okay, so x naught is a constant as far as everybody's concerned. The series sees it as a constant, and we see it as a constant. To us, the variable is x, just like for a function f of x, we think of the independent variable as x. The series thinks of the variable as n, though, and it will change n and update the number, but it just generates a list of numbers, and we think of those numbers as constants, of course, right? But this is called a power series. That's what it is. Now, you might be wondering, well, that's a very strange definition. Why would we define something like that? Well, let me actually write out a few terms of what a series like this would look like, and then maybe you can actually tell me what you might think this might be useful for, what it might look like. So notice here, if I plug in n equals 0, I would get C0. Okay, exciting. Plug in n equals 1, I would get C1 times x minus x naught to the first power. Plug in n equals 2, I get that. Plug in n equals 3, I get that, and so on. Remind you guys of anything? Let me actually do another one, right? This one might be even more suggestive, so let's do another one. Let's suppose the specific constant that I'm picking is x naught equals 0, okay? So let's look at a very specific x naught, right? So this would be the power series for x naught equals 0, right? Because it's x minus 0 all to the n, right? If I start writing out terms of that guy, what would that look like? Well, plug in n equals 0, I would get C0. Plug in n equals 1, I would get C1x. Plug in n equals 2, I get C2x squared. Then C3x cubed. Then C4x4. Then ... going on forever. Remind you of anything? Anybody? What does that remind you of?
a geometric series?
Almost, not quite though. Why would it not be a geometric series? So remember a geoseries. It looks like A plus AR plus AR squared AR cubed plus da da da. So at first you might start thinking geometric series, but the important thing for this geometric series is that you have a constant A, right? Like here you have different C's, right? The C's don't have to be the same in general. So it's not geometric unless I know for sure that the C's are actually all the same number. Something else. It's more elementary. You don't even have to think too hard. In fact, you saw things like this way before this class.
It looks like a polynomial.
It looks like a polynomial. However, it's a very strange kind of polynomial. Seems like a polynomial of infinite degree, right? So if I look at this guy and I say it's a polynomial and someone were to ask me, what is the degree of your polynomial? What is the highest power? The answer would be, there is no highest power. It's just a polynomial that keeps going, right? So this actually reminds us of a very useful function. Polynomials, very useful. Hey, this looks like a polynomial. But then you're like, of infinite degree? What does that mean? I mean, yeah, it reminds me of a polynomial, but is it a polynomial? This is a weird creature, isn't it? Like, does it even make sense to actually write this down? Did I actually write down anything that's actually useful? Can you have a polynomial of infinite degree? That's almost at this point. Remember, when we start to go off to infinity, very strange things can happen. So at this point, you should be pretty concerned with, does it even make sense to write this down? Did I write down something equivalent to dividing by 0? I know I can write down the symbols divide by 0 on a piece of paper, but it doesn't mean that it makes any mathematical sense. So yes, this reminds me of something that is very useful and dear to our hearts. But just because I can actually write it down on a piece of paper, does it actually mean it makes sense at all to actually say this? Is there any such thing as a polynomial of infinite degree? What would that even look like? What would that behave like? How can we use it? So many questions. Okay, so that is, however, as you can probably tell, that is kind of the point of what a power series is trying to capture. It's pretty much a representation of an infinite degree polynomial. But we write it down as an infinite series. Now, why is it called a power series? More power. No, it's called a power series because x to the n is called a power function, right? So that's why it's called a power series. You know, math people and naming things, right? So we look at x to the n, we call that a power function, right? So y equals x to the 5th is a power function. Y equals x to the 7th is a power function, right? So if you have a series of terms like this, we call it a power series. Okay. So that's where the name comes from. So it's pretty much like a series of power functions that's going on forever. Now, it looks like it might be useful, but what does it actually mean? What does it all mean, Basil, right? So before we actually talk about that, what would it mean? Does it even make sense to write this down? Let's look at something that is very, very useful. So this is a theorem, as we mentioned. To talk about series and whether a series is meaningful, it's kind of the same as talking about whether this would converge to something meaningful. So I know that I can't actually write down or add or compute a polynomial of infinite degree. So the idea is, in theory, if I could, would it add up to something meaningful? Would it add up to something that's equivalent to a polynomial in some sense? And so now we have to worry about whether this makes sense. We now have to worry about, is it possible for it to even converge to something? So convergence is an important idea. So we now move on to the convergence of power series theorem. It turns out for a power series, there are only 3 possibilities for its convergence. So it turns out we know very well how, if, or when a power series converges. And the short answer, surprisingly, is it always converges. A power series will always converge. It's just a matter of where. So when it comes to a power series, there are three possibilities for convergence. It's going to converge only for the variable, if I input the variable x, right? It is going to converge only if my x equals the x naught, that same variable that we're centered around from the definition. So your series might only converge at that point, right? So well, I'll talk about that later, right? So that's one possibility, okay? Another possibility is whenever you write something down like this, it is going to be a bona fide function where you can literally plug in anything for x and it will actually work, right? So one possibility also is that it converges for all real values of x. So I have this infinite polynomial and I can plug in any x I want and it's going to work. That's a possibility. It will actually make sense somehow. A third possibility is that it's not going to work for everything, but it's going to work on a certain interval. And it's going to work at an interval in which x naught is going to be the center point of that interval. And that's where the language here comes from. So earlier when I defined it, we defined a power series centered at x naught in parentheses. And that language really comes from this third possibility here. So it's possible that it will only converge for one particular x value. So only if I plug in x equals x naught, but any other thing I plug in for x, it's not going to work. It's possible for any real number I plug in, it's going to actually work and make sense. It's also possible for there to be some interval of finite length for which it will make sense. And that length, I can describe it as having a radius big R, right? So it will be from x naught, a distance r in either direction. My series will actually make sense in that window, right? This window here is called the interval of convergence, and the length, half the length of that window is called the radius of convergence, okay? So let's actually focus on case 3 a little bit more. I want you to appreciate that this is basically what it's saying, right? Here I put a strict inequality because it's not always guaranteed to work at the endpoints. So you may or may not include the endpoints. So whenever I write this, we know because of the properties of absolute values, I can expand it to look like this, right? So there are various possibilities in case 3, right? It can work at x naught minus something to x naught plus something, but it doesn't work at the endpoint, so I put open parentheses. Or it can work at the left endpoint, but not at the right endpoint, or it can work at the right endpoint, not at the left endpoint, or it can work at both endpoints, right? However, very important things to know is that whenever we converge for some set of x values that is not just x naught, the convergence is absolute, and that's going to be very important. We already know that that's pretty important, but it turns out that we will have absolute convergence. The endpoints are not guaranteed to converge. They may converge, in fact, conditionally. However, we are guaranteed to have absolute convergence in these 3 scenarios. In one of these 3 scenarios, right? So for a particular series, only one of these scenarios will work in general, right? Of course, we're going to start to find ways to examine that. Okay, so I already mentioned what the interval of convergence is, right? So the interval of convergence is just that interval, x minus x naught less than big R. R is called the radius of convergence. One or both of the endpoints may be included, and we can sort of extend this, right? So I can talk about R equals 0. And what that means is I'm not allowed to move any distance from x naught. And so my x has to be equal to x naught in that situation, right? So that's the case. That's pretty much case 1 here, right? So this here is case 1. R equals infinity is how we would describe case 2. Now for case 3, your big R is going to just be equal to some real number, some finite real number, right? And our goal, would we want to know what that real number is so we can tell where this little thing that we wrote down would actually make sense. So let's actually illustrate this. So let's look at case one. Basically, so case one. So I have some power series. That gives me C0 plus C1 x minus x naught squared x minus x naught plus C2 x minus x naught squared plus dot dot dot. And we might ask the question, for which x values does this converge? And we have the possibilities. The possibilities are there are three. So case one. So here is the real line. I can have a point x naught on the real line, and my series only converges there. So if I'm at that specific point, we're good. Nowhere else, right? So boom. Series only converges here. In this case, I would describe this as R equals 0. So that's my radius of convergence. And I would actually say the interval of convergence, depending on how much details I want to go into, I might say it's undefined. Or I might just say it's literally only the set that contains x naught. It's not really an interval at all. It's literally only one point where this guy's going to work. So that's case one. Case two. So here I'm on the real line. This is some point x naught. And I would ask, what x values on the real line am I allowed to plug in? Well, one possibility is, plug in whatever you want. It'll work everywhere. Right? I can describe this scenario by R equals infinity. And the interval of convergence is the entire real line. Meaning, no matter what x value you want to plug in, take your pick, this series is going to actually converge to something meaningful. And now comes the third case. In many cases, the most interesting case. It might not converge only for one point or for all points, but there will be some finite window, a window of finite length, and the half of this length is called R. So let's say here R equals K. So it's a window that's centered at x naught. X naught is smack dab in the middle. I can move to the right by a distance K. I can also move to the left by a distance K. So this brings me to the point x naught plus K. This brings me to x naught minus K. And it will converge absolutely everywhere in that window. Now, at the endpoints, at the specific value x naught minus K and x naught plus K, it may or may not converge, but I know for sure absolute convergence will happen within this window. And in this case, I would be able to say R is K, and my interval of convergence is going to be, well, x naught minus K to x naught plus K, where the endpoints may or may not be included, where one or both endpoints may, not necessarily, you have to test for it, included. Okay, so this is just me illustrating like on a real number line when things would actually work out, how it would actually, what does it actually mean? Now, of course, if it's the first time you're ever seeing power series, it's probably still a little bit kind of strange. What are we talking about? But you'll get more used to it as we go on. Okay. But those are the three possibilities. A power series is always going to converge. The question is just a matter of where. Does it converge at a single point? Does it converge no matter what? Or does it converge in a certain window? In which case, I have to specifically test the endpoints to see if it doesn't converge at the edge of the window. But one of these possibilities must happen, right? So that's a theorem that we know, right? I'm not going to prove it, but we know that for sure. Okay, so now let's talk about how do you go about figuring this out? How do you find the radius of convergence and the interval of convergence? And the answer, at least for Calculus 2, for this class, is always the same, the ratio test. You'll always use the ratio test. That's always going to be the ratio test, right? So now you might say, well, why would I always use the ratio test? You don't have to always use the ratio test, but in a Cal 2 class, that's what we're going to do. Why? Well, remember what the ratio test actually says. We have absolute convergence under a very specific situation, right? So the ratio test says we have absolute convergence in the event the limit as n approaches infinity of Cn plus 1 x minus x naught to the n plus 1 over Cn x minus x naught to the n is less than 1, right? So I'd literally plug in my an plus 1, my an, and if I can make sure that limit is less than 1, it will converge. Now, what you'll notice is that this will actually become, well, here you'd be able to actually simplify a little bit, actually. And you'd have something like just a limit as n approaches infinity of something like Cn plus 1 over Cn times x minus x naught less than 1. And so basically you'd have x minus x naught is less than 1 over whatever this limit is. Right? So this automatically gives you an interval. Naturally arises. Right? Now, the ratio test isn't the only one that will give you a nice interval. The root test also gives you a nice interval, and in general, it would be a possibility. But for this class, the ratio test is always what I would expect you to use. It's always the ratio test. It's never any other test. Always the ratio test. Write that down in red, underline it, write it in all caps, right? If I ever ask you, determine the radius of convergence and interval of convergence of this series, it's always using the ratio test, always, okay, right? I'm not going to tell you that you should use the ratio test. This is just something you should know. I'm going to use the ratio test in this scenario. Okay. Let's actually look at some examples. Okay. So here are some power series, and we'll actually get to that pretty soon. We're going to find the radius of convergence and interval of convergence of some power series. Okay, so this is a power series. Okay, how do I know this is a power series? Well, notice that this guy is equal to, plug in n equals 0, I get 1. Plug in n equals 1, I get x. Plug in n equals 2, I get x squared. Plug in n equals 3, I get x cubed. Plug in n equals 4, I get x to the 4th plus dot, dot, dot. So this means it's like my Cn is just 1 for all n. And my x naught is 0. And if I write that out in my formula, right, that's what this guy is. This is the same as saying 1 times x minus 0 to the n. So it's in the form of a power series. It is a power series. Now, I might ask you the question, where does this series converge? For what x values does this converge? What is its radius of convergence and interval of convergence? Now, just to give you an idea of what does it even mean to ask that question? I'll give you some examples. Here's an example. If I plug in, let's say I plug in x equals 0, then this means the series equals 1, right? Look at the above, 1 plus x squared plus x cubed plus x to the fourth going on forever. If I were to go for all those x values and plug in the number 0, notice that I would have just 1 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. So that's going to add up to 1, which makes sense. 1 is a very nice bona fide number. Yeah, that makes sense. Does it make sense for all x values? Let's try another one. What if I were to try x equals a half? Right? What would that series look like? In this case, the series would look like 1 plus a half plus a quarter plus an eighth plus.
Is this geometric?
This one is geometric. Yes, that's something I'm going to ask about later. But yes, it is a geometric series as written now because your Cn is the same number for all n. Now this series is geometric itself, and in fact, this one that we looked at, it's our old dichotomy paradox. We know that this equals 2. So again, it makes sense. Now you might be thinking, oh, well, this guy's a really nice series. I can plug in anything and it's going to actually make sense. In the first case, I plug in x equals 0 and it works out. It adds up to 1. If I plug in x equals a half, that also works out. It adds up to 2. Here's another example. If I were to plug in x equals 1, what would happen to the series at x equals 1? If I plug in x equals 1, what happens?
Wouldn't it diverge?
It would diverge. Notice that if I plug in x equals 1, I would get 1 plus 1 plus 1 plus 1 plus it's infinity. Diverges. Makes no sense. Right? It doesn't make sense as a bona fide real number, right? So this is the kind of question, hopefully that helped you appreciate what kind of question I'm asking. When I ask for the radius of convergence and the interval of convergence, and you write down an interval, basically is what the question I'm asking is what x values am I allowed to plug in? And clearly here, it doesn't work for all x values, but it also doesn't only work for one x value. I found 2 x values for which it works for. So clearly in this case, I'm in case 3, right? I'm in the case where there's going to be a window of x values for which this thing works. Now the goal is, what is that window? For which x values would work? What is the endpoint of that window? Does it work at the endpoint? What x values am I allowed to plug into this power series where the series is going to make sense as a function, as I can plug in x values and I can compute something, I can get an output, and it's going to make sense, right? Because in that situation, then yeah, I probably can think of this as some sort of polynomial, right? Because just like with a polynomial, it has a certain form and I can plug in a number and get an output, right? For all intents and purposes, you can kind of treat this just as you would any other function. Now, the implications of that we haven't touched on yet, but that's kind of where we're going, okay? So clearly this can work for more than one x values, but not all x values. Where would it work? So this is what it means to find the radius of convergence or an interval of convergence. So let's actually jump into it. For radius of convergence and interval of convergence, what do we use?
The ratio test?
The ratio test. I love how you said that. Like it was. It's always the ratio test. In this class, it's always going to be the ratio test. What does it mean to apply the ratio test? Well, for the ratio test, we look at L, which is the limit as n approaches infinity of an plus 1 over an. I need to make sure that that guy is less than 1 because the ratio test tells me that that converges absolutely. Notice that at the endpoints, the ratio test does not guarantee convergence, which is why we're not sure about the endpoints. We have to actually check those individually. What would that look like here? Well, my series is x to the n. So I'm literally going to plug in x to the n plus 1 divided by x to the n. That's not so bad. That's going to simplify to just x. Now remember, the limit is for n. So what is the limit of absolute value of x as n approaches infinity?
Just the absolute value of n.
It's just
x.
It's just the absolute value of x, right? So this limit goes to the absolute value of x. Now, what do we need to guarantee convergence? So what we're going to do is we're going to set the absolute value of x less than or equal to 1 for convergence. In fact, it's going to be absolute convergence. So that now gives me a window. I know my x has to be between -1 and 1, and I have absolute convergence. Now the question is, what about at the endpoints? We already saw that plugging in 1 didn't make any sense, but just to show you a complete example, let's actually go over that. So now what I would do is I would check, and by the way, this tells you here that r equals 1, but we'll see another way to determine this later. Okay, because my r is defined as the guy that I bound the interval by, right? So x minus x naught is less than r. Here my x naught is 0. So this just becomes absolute value of x less than some number. It's less than 1. So r is that number. R equals 1. But we'll see another way to determine that later on. But for now, just notice that this is the interval that we have absolute convergence. What we're going to do is we're going to check the endpoints. So what I'm going to do is when x equals -1, what happens? Well, I'm going to go back to the series. It was just a series of x to the n. That series would now become -1 to the n. That is just going to be, well, 1 minus 1 plus 1 minus 1, converge or diverge? Hello?
Wouldn't it diverge?
It would diverge. How do you know?
Because you wouldn't get to a value as you keep adding and subtracting 1.
No, that kind of argument won't work. It's a math class. When it comes to talking about series convergence, you have to do a series convergence test. So yeah, knowing series convergence tests, you have to know it like the back of your hand for this problem, because you're going to have to just do it on the spot at some point. Tell me mathematically how you can know this diverges.
The limit as n goes to infinity is not 0, so it
Right.
fails
This diverges by test for divergence. The limit of an is not 0. When x equals 1, my series would become just the series of 1 to the n. plus 1 plus da da da. Notice this also diverges by test for divergence because the limit here is 1, non-zero. So here, the limit of an does not exist. Here, the limit of an equals 1. In either case, it's not 0. That's the important part. Now here's something nice. I'm going to leave some more examples for you guys to do. So I'm going to have you guys do this for next time. But before that, let's actually just move down to this. And I'll cover this because someone already mentioned something, which makes me think you guys will already kind of see it. So here's the thing. I know this converges. Oh, I didn't actually put the answer. Let me actually write that down. So the interval of convergence here is -1 to 1, not including -1 or 1. And the radius of convergence is 1. So that's the final answer. Now, how do I know that that's the radius of convergence? A couple ways. Either you can tell from the formula earlier, or I know that at 0, this goes from -1 to 1, and the radius is just half that length, right? So here r equals 1. The max length is 2. Radius equals 1/2 the length. So if you want to find the radius of convergence, you can first find the interval of convergence and just take half the length of that interval, or just realize that once you can write it as x minus x naught in absolute value less than some number, that number is going to be your radius of convergence. So in this case, we have this series, the series of x to the n goes from 0 to infinity. It converges absolutely within this interval. I can plug in any x value I want between -1 and 1, and it will converge absolutely. It converges with a radius of convergence equal to 1. So the question is, what does this converge to? That's the follow-up. So this is 1 plus x squared plus x cubed plus. If I were to ask you, what does that converge to, right? I know it converges, but it turns out we can determine what it converges to. What do you think?
1 over 1 minus x.
1 over 1 minus x. How do you know?
Literally, and
It's a geometric series, and the first term is 1, and our
It's
common
geometric.
ratio is x.
This guy is geometric. Someone mentioned that earlier. Here, your a equals 1 and your r equals x. So this converges for r, which is equal to x, is less than 1 in absolute values, which makes sense. We've already verified that earlier. So it's nice that that actually coincides. We're kind of tying things together, which is pretty awesome. And so we know this guy, we actually know what this converges to. It converges to 1 over 1 minus x, right? That's your a over 1 minus r. In other words, I can think of this infinite series, this power series, I can actually think of it as a function once I'm within a certain window. If I look at the function y equals 1 over 1 minus x, right? So I'm looking at this function. what would that look like? Well, at x equals 1, it has an asymptote. And it would look like that and that. So basically, I know between -1 and 1, which means it's this part of the function right here, we can think of this part of the function as an infinite series. And so now, hopefully you're starting to appreciate where we can actually go with this. I can, in some sense, and this is something I'm going to justify further, this guy and that guy are the same whenever I am within a certain window, whenever I'm in the radius of convergence. I can think of these two as one as the same. They're interchangeable, right? Now that's something I'm going to have to justify a little bit more, but that's essentially where we're going. The idea is power series are going to be very useful in the sense that we can actually use the series to represent functions. And on one hand, you might say, well, I'd rather represent it like this. Like, why would I want something as complicated as this? Well, there's always going to be a reason, right? If we can write something in multiple ways, and I'm like, hey, here's a way that we can write this thing as, there's always going to be a reason why we might want to write it at that way. And you're going to realize that there are going to be times when we want to actually rewrite a function as a series. And we're going to be able to do all sorts of things with that series that we wouldn't have been able to do with a function. And so that's where we're going. We will pick up with that story next time. But in the meantime, I will leave this here for you guys to do. Try for next time. Find the radius of convergence and interval of convergence. Find IOC and ROC. Okay. So power series, just introduce a very, very important guy. At this point, you probably don't even appreciate why it's so important, but we will start to uncover that mystery pretty soon. So that's the idea of a power series, where they work, how to figure out where they work. And just as a curious example, it turns out here's a power series, and it actually converges to something that is familiar to me, a regular old rational function. As long as I'm within a certain window, I can think of this series as that function, which is more useful than you know. A lot of times you're plugging things into your calculator or Wolfram Alpha, and from your perspective, you're plugging in some function f of x, but in the background, Wolfram Alpha converted that thing to a series because it's much easier to work with series for certain things. And so it converts the answer to a series. It'll find the answer. It'll use the estimation technique that I mentioned to you guys earlier to approximate the answer within a certain degree of accuracy, within a certain number of decimal places, and it will actually output the answer on the screen. And you might be thinking, wow, Wolfram Alpha knows how to integrate and differentiate this thing and plug in a value and find a critical point. When actually, all Wolfram Alpha did was add up a bunch of terms and plug in a number and estimated it with a partial sum. So that is pretty cool. On my screen. Screen spazzed out on me for a second there. But yeah, hopefully that was pretty cool. We'll pick up with that next time. Try these examples for next time. I'll leave them in the notes, and we will stop there for now. I also remember I have office hours with one of you, and I will send you that link shortly. So that's it. Hopefully you understand everything. Thank you for your attention. Thank you for your time. And I will see you guys in the next.